The detection of latent fingerprints at the scene of crime is a very important step in forensic science. It helps us in elucidating or establishing the identity of the criminal. There are several methods which may be used for detecting latent fingerprints at crime scenes. In many of these methods, metals as well as metal ions play a significant role. Many of the compositions which detect latent fingerprints are based on metals, and some of them are based on metal ions as well. The most trivial example is aluminium powder. It gives very good quality fingerprints on a large number of crime scene evidence. Of course, the aluminium particles must be homogeneous, they must be small in size, and very often they may be coated with some fluorescent dyes. When they are coated with fluorescent dyes, the powder constituting the aluminium particles and maybe some other reagents also, it helps us in detecting faint and fragmented fingerprints as well as fingerprints on multicolored items. Apart from aluminium powder, many other metal powders can also be used. In fact, iron powder, very small particles of iron, they help us in preparing the magna powders, or also called magnetic powders. The significance of these powders is that they may be used on vertical surfaces like almirahs and refrigerators. Silver nitrate is another good method for detection of latent fingerprints. It's based on the premise that sweat residue contains chloride ions. Silver nitrate reacts with the chloride ions to give white but unstable silver chloride. When exposed to sunlight or ultraviolet light, silver chloride decomposes into finely divided black silver particles, and so black colored finger ridges are rendered visible. Metal ions are not directly used in Ninhydrin method, which is also one of the most popular methods of fingerprint detection. Yet, when the contrast is not very good, metal ions may be used as post-treatment reagents. For example, the Ruhiman purple, the complex which is formed on the ridges once the fingerprint residue is treated with ninhydrin, reacts with zinc chloride or cadmium chloride and produces a very stable complex which is fluorogenic in nature. When exposed to laser light, it enhances the ridge characteristics. Yet another technique which uses metals is the multi-metal deposition, where a successive layer of gold particles and silver particles is formed on the fingerprint residue. The mechanism is that the protein content of the sweat and even the amino acids, they absorb gold particles, and gold particles in turn absorb silver particles. These days, nanotechnology-based fingerprint detection techniques are also becoming very popular. We may use nanoparticle size copper, we may use nanoparticle size aluminum oxide, and some of the times we have used even nanoparticle size calcium carbonate. Nanoparticles have got very large surface area, and if most of the sweat residue has evaporated due to hostile weather conditions, the nanoparticles still help us in detecting those weak and fragmented fingerprints. Apart from this, there are several compositions which use meshed metals, and they have got very long shelf life. Moreover, such compositions can be used both in the laboratory as well as in the field. They pose no occupational hazard to the users, and they are cost effective.
Dear students, after studying this module, you shall be able to know that metals constitute a significant component of several fingerprint reagents, and you'll understand that metal ions play an important role in several fingerprint detecting methodologies. Apart from that, You'll also come to know that metal complexes are important both as fingerprint reagents and post treatment chemicals. You see, there are a host of chemical methods for detection and enhancement of latent fingerprints. Those which involve the use of metals or metal salts are reviewed in this module. So basically, it may be claimed that there is no more effective deterrent to a crime than the certainty of detection. Equally true is that there is no surer way of establishing identity than by fingerprints. The detection of latent fingerprints at the scene of crime and their subsequent development is therefore one of the most powerful tools available in casework investigation. The fingerprints found at the scene of crime or an article removed from it is formed when the papillary ridges leave a deposit of perspiration on a surface with which the finger has been brought in contact. The palms of hand are endowed with frictional ridges, also referred to as papillary ridges, which assist in holding or grasping an object. The ridges are studded all along with minute openings called as sweat pores. As the name implies, sweat continuously oozes out of these pores. When the finger touches a surface, it leaves behind a deposition of sweat exactly in the same manner and pattern as the ridge design. However, this deposition is not visible since sweat is colorless. Hence, it is called a latent fingerprint. The latent fingerprints found at crime scenes are rendered visible by an array of chemical methods. In many of these methods, metals or their salts play a significant role. Now, let us have a look on different methodologies. First comes powder method. The simplest and most commonly used method for detecting latent fingerprints is the powder dusting. This technique relies on the mechanical adherence of the detecting composition to oily components of sweat. While selecting the powder, it is must to ascertain that its ingredients do not interact chemically with the surface bearing the latent impression, nor should it be strongly physically attracted to the surface. Powder formulations containing meshed metals have also been used for a considerable time. These have relatively long shelf lives. Silver powder containing aluminum flake and pulverized quartz, gold powder containing bronze flake and pulverized quartz, and gray powder containing meshed aluminum and kaolin are some examples of metallic dusting composition. In here, the figure a fingerprint developed by a metal based composition on glossy magazine cover. A good number of powder formulation contain metals or metal salts in concentration with organic derivatives that fluoresce or phosphorese upon exposure to ultraviolet or laser light. The advantage of such compositions is that these are useful for visualization of latent prints impinged on multicolored surfaces that would present a problem of contrast if developed with regular or metal based powders. Moreover, these may be used for detecting weak, chance, and fragmented fingerprints that are often encountered at crime scenes. Their disadvantage is that these can rarely be used in fieldwork. Some common organic compounds that have been used for preparing luminescent powders are rhodamine B, acridine orange, and crystal violet. A latent fingerprint developed on paper under fluorescent conditions is depicted in this figure. Then comes nanotechnology-based methods. Conventional fingerprint dusting powders pick up prints since the oil secreted by fingertips has a natural tackiness. In the course of the time, the oil tends to evaporate, and therefore all fingerprints are difficult to detect by powder method. This problem is specifically relevant to a tropical country like India, where hot climate prevails 8 out of 12 months in a year. Nanotechnology provides a solution to this problem. Nanoparticles have the ability to actively seek out oil from the fingerprint residue, however small the amount may be. This paves the way for development of even extremely faint fingerprints. The adhesion of a powder formulation to fingerprint residue is governed by the pressure deficit mechanism. If a powder particle is wetted only on its lower side by the sweat deposition, then owing to the curvature of the meniscus, there will be a pressure deficit inside the droplet, causing the particle to adhere. The electrostatic attraction between the sweat residue and the powder particles too play a role in adhesion, albeit a minor one. The effectiveness with which the powder adheres to the ridges depends on the size and shape of the particles that compose the formulation. Small fine particles adhere more easily than large coarse ones. Particles with size in nanometer range have excellent adhesion ability. Hence, as shown in the figure, the nanotechnology-based compositions develop clearer and more detailed fingerprints as compared to conventional powder formulation. Fluorescent fingerprint dusting compositions based on nanoparticles of metal salts in concert with eosin Y dye have shown promising results. These develop finger marks on a broad spectrum of items. It has been observed that better quality fingerprints are obtained when nanoparticles of a polar metal salt rather than of a pure metal or an alloy is used as the base material for preparing the composition. The reason being that the quality of developed fingerprints was profoundly affected by the degree of attraction between the adhesive material and the colorant. Stronger the interaction, better is the quality of the developed fingerprint. The attraction between the adhesive and the colorant, in turn, is dictated by dipole-dipole forces between the two chemical entities. Eosin Y is a polar species with a small positive and negative charges residing on carbon and oxygen atoms, respectively. In its molecular structure, alumina 2 is a polar molecule in which a partial positive charge resides on aluminium, with a partial negative charge resides on oxygen. The dipole-dipole attraction between alumina and eosin Y is substantially large. On the other hand, there is no charge separation on the nanoparticles of copper. The dipole-dipole attraction with eosin Y is concomitantly small or altogether absent. For this reason, the fingerprints developed by alumina-based composition are clearer and sharper as compared to those detected by copper-based composition. A comparison of fingerprints developed on glass by alumina containing formulation and copper containing formulation supports this assertion. Another useful method is Ninhydrin method. Ninhydrin treatment is one of the premier techniques for development of the latent prints on porous surfaces such as paper. Ninhydrin react with amino acid content of sweat, forming a purple complex called Reuman's purple. However, the concentration of amino acids in sweat is quite low, as a result of which the developed prints do not show sharp contrast. To improve the clarity, prints are post-treated with salts of group 12 elements of the periodic table. This results in conversion of non-fluorescent Reuman's purple into a photoluminescent complex. The color of ninhydrin developed fingerprints changes to red or orange on post-treatment with zinc chloride or cadmium nitrate. Subsequent observation under an argon ion laser produces appreciable luminescence. The intensity of photoluminescence increases at low temperature. Reuman's purple is an active chelating agent and forms colored coordination complex with variety of metals. Spectroscopic studies coupled with X-ray diffraction analysis have revealed that such complexes contain metal iron and Raman's purple in the stoichiometric ratio of 1:1. Further models of structural and photophysical features have been developed to establish guidelines for the formation of fluorescent metal Raman's purple complex. Treatment with methyl thionanhydrin followed by reaction with zinc ions produces more intense fluorescence than that obtained by using ninhydrin alone. However, post-treatment with cadmium ion gives better results with ninhydrin. Likewise, several ninhydrin analogues including 5-ethoxyninhydrin, 5-ninhydrin and benzofuranninhydrin give optimum results after the latent prints have been post-treated with zinc salts. Then comes vacuum metal deposition method. Vacuum metal deposition, a technique largely used for development of latent fingerprints on non-porous surfaces like plastics and polythene, involve successive deposition of gold and zinc under low pressure. Normally, zinc deposits uniformly throughout the surface except where fingerprints are impinged. This results in development of negative prints in which ridges remain transparent while the background is plated with the metallic zinc. Vacuum metal deposition is an extremely sensitive technique for old prints, as well as for prints exposed to adverse environmental conditions. Beside the gold zinc mixture, a number of other metals may also be used in this technique. For example, a mixture of zinc, antimony, and copper gives optimum results even up to a temperature of 1540 degrees Celsius. On polythene items, a slower rate of evaporation of metal or metals favors effective deposition and development. In case excess gold gets deposited, the coating of zinc is hindered. However, if air is admitted in the chamber, the gold clusters get smoothened. The quality of developed prints is influenced by the type of polymer surface as well as by the age of the donor. Vacuum metal deposition detects 11% more fingerprints than DFO on paper samples less than 21 days old. Small particle reagent method, an aqueous suspension of an insoluble powder in a surfactant may be used to develop latent fingerprints on wet surfaces. It fixes the lipid content of the fingerprint residue. Conventional small particle reagent formulation is a suspension of dark gray molybdenum disulfide in molybond detergent. Small particle suspension of black iron oxide powder gives prints with good contrast on smooth surfaces. Zinc carbonate based formulation is used for developing prints on dark and wet surfaces. A fluorescent small particle reagent may be prepared by adding basic yellow 40 dye to the stock solution of conventional small particle reagent. The developed prints may then be visualized at 450 nanometer. Another novel formulation containing suspension of black and silver fingerprint powders in a dishwashing liquid has also been found to be effective. A combination of basic zinc carbonate with eosin Y dye gives a small particle reagent that can detect fingerprints on non porous items that have remained suspended in water for up to 36 hours. Cyanoacrylate fuming is a good alternative to small particle reagent, but it works well only on dry surfaces. On the other hand, a titanium dioxide based formulation of small particles is known to develop white imprints on moist plastic, glass, and metals. The technique is also effective in detecting finger marks on soaked firearms. Then comes physical developer method. A physical developer composition normally consists a mixture of a reducible metal salt, a reducing agent, and a buffer. Most formulations incorporate silver nitrate as the metal salt. It reduced in situ to metallic silver which becomes adhered to the fingerprint residue. When latent fingerprints are required to be developed on paper, the alkali content of the latter must be neutralized by pre-treatment with malic acid. Prints may be intensified by hypochlorite treatment. The performance of the technique is dependent on the quality of water used for preparing the formulation. A variant of physical developer involves a modified two-step procedure. First, the sample is treated colloidal gold and next it is sprayed with the physical developer solution. Another variation of physical developer, the multi-metal deposition, has immense potential in detecting finger marks on non-porous surfaces like beer labels and gloves. The effectiveness of the multi-metal deposition method depends on the particulate size of the solute and the pH of the stock solution. A modified version of multi-metal deposition has been found to be effective on a number of semi-porous surfaces such as latex gloves and wax paper. A dilute physical developer solution may also be used to enhance silver nitrate developed fingerprints. Now, let us talk about silver nitrate method. Silver nitrate is one of the vintage methods used for the development of latent fingerprints and is most suited for porous surfaces like paper and wood. The reagent fixes the sodium chloride content of sweat, leading to the formulation of silver chloride. The latter decomposes into finely divided silver by the action of sunlight or ultraviolet radiation. The metallic silver gets deposited on the ridges, rendering these visible. A solution of silver nitrate in ethyl alcohol has been used for enhancement of faint marks developed with ninhydrin when used in conjunction with iodine silver plate transfer technique. The reagent develops latent fingerprints on human skin. While using the silver nitrate method, care has to be taken to avoid overdevelopment of prints. This invariably leads to background coloration. Then comes lanthanides and actinides. Complexes of lanthanides and actinides finds application in the detection of latent fingerprints. The rare earth metal ions form colored fluorescent chelates with Raman's purple, the reaction product of ninhydrin and amino acids. For example, europium chelates produced by the reaction of europium ions with aryl beta diketones are fluorescent in nature and are of help in detection of latent fingerprints on the human cadaver skin. Europium complexes also impart luminescence to print pre-treated with cyanoacrylate. Both europium and terbium ions on compilation with Raman's purple produce luminescent derivatives. Lanthanides are useful for lifting fingerprints on currency notes as well as on conventional porous and non-porous surfaces. A few European chelates serve as fluorescent, lipid-specific follow-up reagents after the fingerprints have been developed by ninhydrin or DFO methods. Europium complexes have also been used as one-step reagents for luminescent investigation of latent prints. Old fingerprints on porous surfaces may be developed with lanthanide complexes in concert with protein stains. Then let us discuss various miscellaneous methods. Metals also find use in some of the unconventional methods of latent fingerprint development. For example, a DC initiated metal sputtering process involving copper, zinc, platinum, and gold gives satisfactory results. Metal flake powders of aluminium, zinc, copper, and iron too have been used for detection of latent fingerprints. Similarly, using milling procedures, aluminium, brass, copper, zinc, and iron flake powders were manufactured for detecting finger marks on light backgrounds. The quality of developed prints depends on the milling condition. Commercially available SB black powder has been used for the detection of latent prints on the craft adhesive tape. Cadmium sulfide, commonly used as a photoluminescent semiconductor, may also be employed as a fingerprint reagent. Now, let us summarize this chapter. In this chapter, we have learned that metals have played a profoundly important role in detection of latent fingerprint. There is a very large list of fingerprint reagents where metals in elemental state, not complexes cationic state and complexes state, have interacted with sweat residue and developed clear and sharp impressions. Metal derivatives have also been used as post treatment reagents to enhance weak and faint chance prints, which are often encountered at crime scenes. A good number of metal coordination compounds impart fluorescent characteristics to develop fingerprints and hence in their detection on multicolored crime scene evidences.